Welcome back, everyone, to the second day of the second week. I just want to make a quick announcement earlier in public schedule. So if you're looking at old schedule, it's slightly outdated. Because we have one additional talk at the end of today at 5:40 to 6:10, so half-hour talk by Sabita Ron. So please stick around for that. Okay, so now it's my great pleasure to introduce Professor Barbara Nelli from University of L'Aquila. She's kindly agreed to give a lecture course. Unfortunately, the timing didn't work out that she could come last week, but she's able to join us this week, so we're very pleased to have her. And the title of the first lecture is Maximum Principle for Elliptic PDE and Geometric Applications.
Okay, thank you very much. Is this working? Yeah, I think so. So let me first thank the organizer for inviting me to this very nice place. It's my first time in India, so I really appreciate it. And my course will be about, in fact, it will be about minimal surfaces, so very in the title, because it's maximum principle for geometric PDEs. And the geometric PDEs include the minimal surface equation. So let me just, okay, we are in a minimal surface meeting. So everyone knows that a minimal surface, I'm just recalling something about that. A minimal surface locally can be seen as the graph of a function over a domain that satisfies this equation. The divergence, let's say if it is a minimal surface, let's say for the moment in R3, really a simple one. So this is the divergence in R2, and this is the gradient in R2. Everything is in R2 equal to 0. This is the minimal surface equation, the general one. In fact, this you can extend a little bit and write that this is 2h over w to the power 3, where wu is usually this stuff. Okay, so where h is the mean curvature. That is the sum of the principal curvature divided by 2. Okay, these are the principal curvature of the surface. Okay, this is really very easy. Is a basic course in differential geometry or surfaces in R3, but you can generalize this kind of notion to any hypersurface in a Riemannian manifold. In fact, you can define a minimal hypersurface in any Riemannian manifold, and you will get that locally you can again write the hypersurface as a graph. You have to define a notion of graph, and then you get a similar equation. So in general, for, let's say, Mn in a manifold, a Riemannian manifold of dimension 1 more, locally, you can write Mn as a graph of a function. Here, everything is a little bit sloppy because graph, you have to define what a graph, but I mean, believe me, there is you can give a sense to all this. A graph of U defined in an open set of Rn, satisfying a similar equation that is the divergence, gradient U over Wu equal to NH over W. like that, where of course you have to use the right notion of divergence and so on. Okay, with suitable, with the suitable divergence and so on. All this just to justify the fact that all the time you have a minimal surface or a constant mean curvature surface, hypersurface or anything, you get a divergence type equation. So you have, and you can prove that it is elliptic. I will give the notion of ellipticity later on. And so to study this kind of surfaces, this kind of objects, it's very important to understand the structure of this equation and the properties that this equation have. What we are going to do is proving a much more general maximum principle that applies in this case. And the geometric way of seeing it, geometric maximum principle, that will be really the way we are going to use it, is something like that. If you have two, let's say minimal, two minimal surface, M1, M2, minimal, that are tangent at a point, so the tangent plane are the same at this point. And if you have that, if it happens that M1 lies above M2 around P, well, let's say there's above M2 in some sense, it's here, yeah? So this is the tangent plane. So the result is that M1 coincides with M2 locally. So you cannot have two minimal surfaces touching at the point being one of one side of the other, okay? And this is more general, but this will be the way we are going to use the maximum principle that we are going to oops, sorry, that we are going to prove. Just a couple of concrete application of this maximum principle that we try to prove. At least one of them we are going to prove at the end. One is, let's say, application in the sense that this will be one of the principal tools for proving the theorem that I'm going to write down now. So one is Alexandrov theorem. That many of you already know, but I will write it down. So if you take M, a manifold in, let's say in Rn+1, even if you can prove it in other space, in particular in the hyperbolic space in the half sphere. So let M be an embedded, compact, hypersurface with constant mean curvature. So it's not minimal, but with constant mean curvature. Of course, I define the mean curvature only for a surface, but if you are in a Riemannian manifold, in particular in Rn+1, you have the connection, you can define n principal curvatures, and then you get the sum of the ki over n will be your mean curvature. It's a simple generalization. So M be an embedded compact hypersurface with constant mean curvature, then M is a round sphere. Okay, really the round sphere. This is, if you think about it in R3, it's a classification of spheres, a classification of a CMC, so CMC, I will call that CMC, yeah, to be quicker. You can see that it is another way of classifying CMC surfaces, like Hopf theorem, for example. Hopf theorem say you that if you have a CMC sphere in R3, sphere from the topological point of view, then it is a round sphere. So here you don't have the topological assumption, but you have the embeddedness that you don't need in the Hopf case. But they are classification theorem that goes in the same direction. So a fundamental tool for that is the maximum principle that I'm going to prove. And then another very nice theorem is the half space theorem. This time is not for compact stuff, but is for minimal and so non-compact. So the half space theorem, just to be, this was more or less in the, let's say, 58 or something like that. And this is 89 or something like that. It's around, yeah? It's around. Okay, and this is Alexandrov, and this is Hoffman, David Hoffman, and Bill Mix. Okay, so the half space theorem, let M be a minimal surface in R3, immersed, let's say properly immersed. So this can have self-intersection, minimal surface. Complete. Non-planar. So it's not a plane. It's very general stuff. Yeah. Then M cannot be contained in a half space. Okay. So if you think on your favorite example of minimal surfaces, I don't know, the classical one, the plane, okay, the catenoid, it's very big, cannot be contained in a half plane. An helicoid cannot be contained in a half plane. I don't know, even properly immersed, or N per surface, or, I mean, I'm thinking about classical example, yeah? Costa surface, none can be contained, and it's a theorem, I mean, cannot be contained in half space, and is basically the maximum principle. Okay, so I hope you're convinced that we need to prove this maximum principle. There are many other applications, of course, but let's try to start. Okay, so I'm going to be very, I'm going to give all the steps of the proof. And in fact, first, I'm going to prove Hopf maximum principle for linear elliptic PDE. That is the one that is the main tool for proving, no, not the main, the tool for proving the maximum principle for more general equation. You see, the equation that I wrote down before for the minimal surface equation is not linear, of course. So you need to work a little bit more. Okay, so second order, let's say maximum principle for second order linear elliptic operators. Of course, I didn't say at the beginning, but feel free of interrupt me at any moment if there is something that you want to understand better. Okay, for this principle, there is a standard reference that is the Protter and Weinberger book. Let me write it down, Protter, Weinberger. And it's, the title is, okay, Maximum Principle for Differential Operators. Okay, so first, we consider a second order differential operator that is something like that. L is equal to sum for ij from 1 to n of aej x1 xn d square dxc dxj, where this is a point of Rn. And without loss of generality, you can assume as this, if you apply it to a C2 function, as this is symmetric, you can assume that the matrix Aj is symmetric. Okay, so L is said to be elliptic. If the matrix, or let's say like that, if elliptic at point x, it's 1xn. If there exists mu of x larger than 0, such that the sum of aej x over e and j times C1, CE, Cj is larger or equal than mu of x sum over E of Cx squared. Okay, that's the same, so mu is positive at the point x. That's the same as saying that this matrix is positive definitely. That's Aj is positive definitely. But this way of writing is useful for us. And then, of course, as usual, L is elliptic in omega if this holds for n x. Let's say that this point is in a subset of Rn. Just to, so L is elliptic in omega if it is elliptic for any x in omega, and then it is a uniformly elliptic in omega if there exists a mu 0 such that mu 0 positive, of course, such that mu of x is larger than mu 0 for any x in omega. Okay, larger or equal, the same. Okay, so you can have many examples, but I mean, example just to see that this is not too strange. So for example, if you take as a matrix axy 1 minus x squared, xy, xy, 1 minus y squared, this is elliptic each point of omega on, let's take omega equal to the disk. So x, y in R2 such that is smaller than 1. So here it's clear that on the disk, let me do an extension. Let me say A is elliptic, but this means that the operator corresponding to this matrix is elliptic. So is elliptic in omega, but not uniformly elliptic. It's very easy to see that you can find points approaching the boundary where this mu0 cannot exist because it goes to 0. Okay, so now let us just say something about now starting to talk about maximum principle. It's an elementary fact that when you have a function, even defining an interval, if you have a maximum at an interior point of the interval, so the derivative is 0, and you know that the second derivative is larger or equal than 0. So if the derivative, wait a minute, I have always to think about that. So yeah, the derivative is less than or equal to 0. So it is, if it is larger than 0, that cannot be an interior maximum. Okay? But one can prove that the same holds with the non-strict inequality. Let me be more precise. Just, I know that I was a little bit confused, so let me be more precise for an elliptic, linear elliptic stuff. So consider, now we know what is elliptic, consider L of U, a differential operator, that has a part like the previous one. So I, E, J, dXc, dXj, U, plus some Bi, du, dxi. Okay, so, and with this elliptic. Okay, now, and U is defined on a domain D of Rn. Okay, and now take x bar in D, a point of maximum for U, local. Huh? Okay, elementary analysis tell you that for any coordinate system that is Z1, Zn in D, any coordinate system that you obtain as a linear with a linear transformation by X, obtain it by linear. You will see in a moment why I need it. Linear transformation of x1, xn. You have that, as it is a point of maximum, you have that du, dzi in x bar is equal to 0, and that all the derivative are, the second derivative are that I square are less or equal than 0. Okay, this is just elementary analysis. Now, in particular, you can do a choice of this zi. It's not hard to convince yourself that you can transform this operator in the Laplacian at that point. So you can choose, this is really linear algebra. You can choose Z1, Zn, such that L is the Laplacian at x bar. Okay, so you see in a moment, you see that then L of u larger than 0 cannot hold x, okay? Because this part is less or equal than 0, and this part is 0 at that point. Okay, but that's the elementary stuff. Now, what you want to prove is that a function, the real maximum principle, the up maximum principle, is that a function cannot satisfy L of u larger or equal than 0 if it has an interior maximum. Okay, so the sharp, in this case, it's very easy, but in this case, you have to work a little bit more. So this is really the up maximum principle. And goes exactly as I told. That is u defining omega in R, satisfying. Of course, I don't tell it, but it has to be twice differentiable and everything, because we are applying a differential operator of degree 2. So satisfying L of u, the same L, so sum aj d square u x dxj plus sum bi du dxi larger or equal than 0. L uniformly elliptic. You need the uniform ellipticity in omega. And you also need ij bi bounded, uniformly bounded. Then, if u has an interior maximum, M, it is u is equal to M everywhere. Then, okay, let me write it like that. If u, then u is equal to M. Okay, so it cannot have an interior maximum. Okay, let us prove it. This is the classical proof by Hopf, and of course I put the assumptions that are very sharp. You need this uniform ellipticity, but you also need that the coefficients are bounded. In fact, one can relax some of the assumption, and the proof is almost the same, but you have to be more careful. So, for example, you can relax the assumption on the boundedness of the coefficients. You just need that the coefficient grows in a certain way. I mean, but I'm not going, yeah. The domain D is any open domain. Yeah. I mean, here you are in a Rn. Okay, this is in a Rn. But you don't need, I mean, when you write down an operator, you can write it in coordinates, so you come up with something like that. Sorry? There is no, you mean plus HU, you mean this part? No, you should not be, it should not be there. There is an important reason for that, but you will see it later, because you need a sign over on that part to get the maximum principle. But then in the general case, we will have a more general maximum principle. This is just a linear one, okay? Okay, so let's prove it. The proof is by contradiction. And it's very, let's say, it's very standard in some sense. One uses all the time the same kind of proof. So probably you already saw that in some cases, but I think it's very important to see it really once. So assume that there is assume there exists a point in, I don't remember, omega, okay, omega. In omega, such that u of p is equal to m, so this maximum, and there is a q in m where it doesn't hold, so u is not a constant, such that u of q is less than m. Q in omega, yeah, sorry. M doesn't exist here. Thank you very much. Okay, M is it's not the manifold. In my mind, M is the manifold, it's not the maximum, but here is the maximum. Okay, okay, so let's do a picture. You have a point P where U is M, and you have this point Q where U is smaller than M. And you take a curve. Here, this is omega. You take a curve gamma in omega, like in the picture. So joining the 2 points. U to M to P. Okay, and so you start in Q. You have that U of Q is smaller than M, so you go along gamma, and you will find the first point R where U is equal to gamma. It can be P in principle, but so let R the first point on gamma such that U of R is equal to M. So for all these points, U is smaller than M for the point between Q and R. And now let us define, we want to define some bolts here around. So we have to define a distance that we can take without going out of omega. So let L, let's say like that, for any L in gamma, we compute the distance between L and the boundary of omega. So you take L, you compute the distance. And then you let D equal to the infimum over all the points L of gamma of the distance between L and the boundary of omega. Okay? So it's the smaller, you take the smaller one. Okay, and you let P1 here between Q and R, so in gamma between Q and R, such that the distance between P1 and R, the distance between P1 and R is less than D over 2. Okay, now, so it's a point here where the distance is small, less than this disk, this distance between gamma and the boundary. Just one, we are going to work. You remember that what we said at the beginning, that if you get this kind of inequality, you are done. We don't have the sharp inequality, we have the larger or equal. But if we find out a function, a suitable function, when you have this condition, that function cannot have an interior maximum. So we are going to work to find such a function that then give us the result. Okay, so we are going to work for this. We are going to work for finding a special test function, what one calls test function. And we need the construction of it is a little bit involved, but not difficult, just involved. Okay, so now let me do a big picture here. So we have Q, and we have this P1 here somewhere. And we are going to construct a disk of radius d. No, we are going to construct the following disk. So let K be a disk around E1. That is the largest. Such that U is smaller than M in K. Okay, remember that you have R here. So here you have that the function is equal to M. So for sure, this disk will be, I mean, the maximum that can be is like that. It cannot be larger than this. Okay. And so as this distance was less or equal than d over 2, this radius must be less than d over 2. So the radius of K is smaller than d over 2. Okay, but on the boundary of K, there is at least one point that can be R, but can be also another one, where the function has value M. So let S on the boundary of K such that U of S is equal to M. There is at least one point. I take it outside gamma for, because one doesn't know, but okay. Now we are going to construct another disk. Let me take S here. Maybe I should do it bigger. So this is R, this is P1, this is the big disk, K, this is S, and I'm going to construct here another ball. This is S. Okay. So I call it, this is K, I call it K1. So who is K1? K1, let K1, the ball contained in K, tangent to the boundary of K at S of radius, let's say R1. Radius R1. Okay, we call it 1. It's contained, so it's there. What we can say about that, we can say that U restricted to K1 is smaller than M, because the only point here where U is M is S. So in the interior, and U restricted to the boundary is smaller or equal than M, except at S. Only one point there, where the value is M. Okay, the last ball, just the last ball that I have to construct. It's a ball centered at S with radius R1 over 2. K2. Okay, last ball, K2, a ball centered at S, radius R2 equal to R1 over 2. I know it's a little bit boring, but it's necessary. Okay, I think we have all the ball now. And then we are in good shape to understand what U does on this last ball, and then defining our test function. Okay. The boundary of K2 can be divided into two parts. One part is inside K1, and one part, okay, good. So one part is inside K1, and the other part is outside. Here. So let me give a name to this part. So let, which is the name here. So let, no. The boundary of K2, no, the boundary of K2 can be divided into two parts. So the red one, that is C2 prime equal to the boundary of K2 intersected to the closure with the closure of K1, and the blue one, C2 prime equal to the other part, K2 minus C2 prime. So one of them, this one is closed, and the other one is open. As a part of the boundary, of course. Okay, so let us see what happens for U on this part of the boundary. U restricted to C2 prime. In fact, U in general is, let's say, this C2 prime is inside K, so U is smaller than M. Okay, because C2 prime is inside K. But then, as C2 prime is a closed set, you can find, you can say a little bit more. So as C2 prime is closed, there exists C larger than 0, such that U restricted to C2 prime is smaller or equal than M minus C. This will be important. Moreover, in general, U restricted to C2 twice prime, I don't know how to call that, is smaller or equal than M, because this holds anywhere. Okay, so now we are going to define the test function. So we call this point, the center of K1, X tilde. So let X tilde, the center of K1. Okay, and define Z of X equal to, it's fine if I write here, you can write it. E to the power minus alpha sum over I of xi minus xi tilde square minus e to the power minus alpha r1 square, with alpha to be chosen later. Okay, so this will be the function we are going to study, and it's not hard to prove. I mean, something is very elementary, everything all the computation here are elementary, in fact. But it's clear then Z is larger than 0 in K1. Yeah, because you have this part, so it becomes larger than 0. Z is equal to 0 on the boundary of K1, and Z is smaller than 0 in omega, was it omega? Yeah, minus K1. Okay, that's really something easy. And also a computation that I leave to do, but it's very simple to do, is that L of Z is, should I do it? Okay, is larger than 0 in K2. This is a somewhat long computation that you must do. It's just doing second derivatives and using the assumption that is AII and BI are bounded, and the operator is elliptic. Okay, here you use the computation using uniform ellipticity. And AII, BI bounded. And here, in order to have L of Z larger than 0, you need to do a right choice of alpha. Okay? And choosing alpha. Choosing the right alpha. Believe me, it's not an art computation. It's something that you can do. So choosing the right alpha large enough. I thought I could do it, but I'm running a little bit out of time. I want to do something else. Yeah. Okay, so, but now what are you going to do with that? I mean, we are not done. No? It just, I think I used this. Okay, now we consider W equal to U plus epsilon Z, where epsilon is a number larger than 0 and smaller than C over 1 minus e to the power minus alpha R1 square. Okay, C was our positive number there, and everything is already been defined. Okay, now we are going to use the maximum principle for W in K2, in fact. So let's see how. First, we evaluate W on the boundary of K2. Okay, first we have to evaluate it on C2 prime, but here it's very, here you have that, so W will be smaller than what? You have that U is smaller or equal than M minus 6C. So you can write it, so remember that U is smaller or equal than M minus C. But then you have that epsilon is smaller than this number. And then you have also that here, Z is smaller or equal than 1 minus e to the power minus alpha R1 square. This holds all the time for Z. And so here you can get that being epsilon smaller than this number. So when you multiply Z by epsilon, you have exactly this. So you have it that W is smaller than m minus c plus c. So it's smaller, strictly smaller than m. Okay. Now 2 on C2 second. Here it's easier. You have that u is smaller than m. And you have that, and z is smaller than 0. So you have that w is smaller than m. Okay, but let's see what happens on S in this interior point of K2. So, but W of S is equal to U of S plus epsilon Z of S. But U of S is M and Z of S is 0, so this is M. So W as a maximum, interior maximum. So W as an interior maximum. And now we are going to finish just telling that what happens for L of W. L of W is L of U plus epsilon L of Z. But this is clearly larger than 0 because L of Z is larger than 0. So contradiction. So we have a contradiction. Why? Because we found a function W that is U plus something such that L of W is positive, but it has an interior maximum in K2. So contradiction. Okay? Good. So let me skip. This is proved. I have 5 more minutes, isn't it? 5. 7. Okay. I will get them, I think. Okay. Of course, you can have a minimum principle as well by applying the same thing to minus u. So this is important because you can use also for minimum. And I want to stress the fact that here, omega need not to be bounded. It's any open subset of Rn. Okay? Because you're not looking at point at the, I mean, very often maximum principle relate relate the value at the boundary with the interior value, but here it's something local. So it's really doesn't matter if omega is bounded or not. Okay, but there is an extension that is about the question that someone asked me before. So generalization. That is the following. If you take, it's no more there, but an operator like as before with the second order part and the first order part plus h, that is something like, let me write it. U is like sum aej d square u dx psi dxj plus sum bi du dxi plus hu, where h is a function, again bounded maybe, and so on. So if you have this larger or equal than 0, and you have h smaller or equal than 0, then under the same assumption as before, bounded, elliptic, and so on, then if u has a non-negative maximum m larger or equal than 0 at an interior point, then U is equal to N. Okay, so there is a maximum principle, but is a weaker one. And the proof is not very different. It's analogous. You have the same test function. You have just to deal also with this part. But it's really more or less the same proof. Okay, now the second generalization that one needs, it's the boundary maximum principle of boundary maximum. Okay. I think we are running out of time to do that. So let me just, I'm not going to enter in details of that. This, I will not give a proof. I will just state it. It's finished. No, okay. Anyway, I'm not going to state that because it's somewhat, I need some more notion, but it will be, if you think a little bit about it, if there is if there is something having a maximum on a boundary point, the derivative must be, the exterior derivative must be increasing, must be positive, okay? So larger or equal than 0, let's say, okay? So this will be our maximum principle. In fact, what you can prove that as here is that the strict, okay, if you have that the exterior derivative is negative, you cannot have a maximum at the boundary. This is very easy to imagine, okay? Because the derivative must be larger or equal to 0. But in fact, what Hopf proved was that the derivative cannot be less or equal than 0. It must be strictly positive, okay? Like in this case. If it is larger or equal than 0, it cannot have an interior maximum. If the L, the operator, is larger or equal to 0, then the function cannot have an interior maximum. The same mode at the boundary. If the derivative is larger or equal than 0, then it cannot, is less or equal to 0, then the function cannot have a boundary maximum. I will state it correctly later. Then, after that, we are not done because this is just the linear case, okay? But, in fact, then it will be very quick. If you take a much more general operator, like the one of minimal surfaces, or much more general, in fact, depending on second derivative in a very involved way, not only like, because in the minimal case, let me write down the simplest equation. It's like minimal surface equation. It's U11 times 1 plus U2 square minus 2U1, U2, U12 plus U22, 1 plus U1 square equal to 0. This is the minimal surface equation in R3, okay? For a function, for a surface, a graph, a minimal graph. That's not minimal, but anyway, the picture was not very minimal. So you see that here, the second derivatives appear only linearly. So it's called a quasi-linear equation, okay? But our maximum principle will be much more general. It's the same proof, in fact, for any. And what you're going to do is taking your differential operator and linearizing it. So you get the linear one, and on that linear one, you use the Hopf maximum principle, and this will give you the maximum principle you need. That is the one that we will use a lot. I think I stop here, and not tomorrow, but the day after tomorrow, I will do all this part that is shorter, there is less analysis involved, and then start with the applications.
For that very nice lecture. Are there any questions from the audience?
Hello, ma'am. So in the definition of elliptic operator, there was a mu, right? Is there any condition or mu, or it can be any function?
Any function.
Okay.
Any positive function. But, for example, as I told you, there is you can have a condition of on the coefficient of your operator, the AJ and BI. I told you uniformly bounded, but in fact, your boundedness can be related to mu. Okay, so for example, it is enough that AJ over mu is bounded. Okay, so this can, if you have a good choice of mu, you can relax some of the assumption. If you can have a good choice of mu.
Any other questions from the audience? Of course, you could always ask questions during the break.